The liar paradox. Everything I say is a lie. At first glance, this statement sounds simple, but if you stop to think about it for a moment, your mind might start spinning in circles. Suppose the speaker utters precisely those words, everything I say is a lie. If that sentence is telling the truth, then the speaker really does lie all the time. Yet that would mean at least this sentence is truthful, contradicting the claim that everything they say is false. On the other hand, if the sentence is a lie, then it's not true that everything they say is a lie, which suggests there may be moments when the speaker tells the truth. But if that's the case, we still have the problem of determining the status of this particular statement. The paradox arises because we can't classify the statement as purely true or purely false without running into contradiction. In other words, the sentence self-destructs in terms of logic. It exposes that certain kinds of self-referential statements don't neatly fit into true or false, reminding us that language and meaning can twist back on itself in ways that defy simple categorization. The ship of Theseus. Imagine an ancient Greek warship. Over time, its rotting planks are replaced one by one until eventually none of the original wood remains. Is this refurbished vessel still the same ship of Theseus? This question has puzzled philosophers for centuries. On one side, the argument goes that as long as the ship's structure and identity remain continuous, it stays the same entity, despite the loss of original material. After all, human cells replace themselves over time, yet we still call ourselves by the same name. On the other side, once every single piece is swapped out, how can we claim any real connection to the original? Now, imagine someone collecting those discarded planks and reconstructing them into a second ship. Which one is the true ship of Theseus? This paradox pokes at our intuitive notions of identity and persistence. It forces us to question whether identity rests in the material that composes something or in the form that something takes. We're left with an unsettling realization. Identity might be less about physical components and more about the continuity of form or function. In essence, the ship of Theseus confronts us with the elusive nature of what we call the same thing. The grandfather paradox. Time travel stories often bring up the grandfather paradox. If you could travel back in time, could you do something that prevents your own birth, like harming your grandfather before he ever meets your grandmother? If you succeed, you'd never be born, which means you'd never exist to go back in time in the first place. That's a mind-bending loop. An action you take in the past erases your own future, rendering the original action impossible. The paradox highlights how changing past events can create logical contradictions. Some theories suggest the universe would prevent you from succeeding in any action that disrupts your own existence, citing timeline protection or cosmic self-consistency. Others propose that your interference would spawn a new timeline or parallel universe, leaving your original future intact, but creating an alternate reality in which you never exist. The paradox points to deep questions about causality, free will, and the nature of time. It underscores that even if we could theoretically move through time, we don't fully understand what that would mean for the threads of cause and effect. The grandfather paradox lingers as a potent symbol of time travel's logical and philosophical pitfalls. Achilles and the tortoise. In this famous Zeno paradox, the swift Greek hero, Achilles, challenges a slow tortoise to a race, giving it a head start. Common sense says Achilles will quickly outrun the tortoise, but according to the paradox logic, Achilles must first catch up to the spot where the tortoise began. By the time Achilles gets there, the tortoise has moved a bit further. Then Achilles has to cover that distance, by which time the tortoise has moved again. And so on, ad infinitum. Each time Achilles reaches the tortoise's previous position, the tortoise has made some incremental progress. Because there are infinitely many such catch-up steps, it seems Achilles can never truly overtake the tortoise. Yet, in real life, Achilles obviously does pass the tortoise. Zeno used this paradox to challenge the notion that continuous motion could be broken down into infinitely many finite segments without creating logical problems. Modern mathematics resolves the paradox by recognizing that the infinite series of distances converges to a finite sum. But the puzzle remains a great illustration of how our intuition can stumble over the idea of infinite subdivision. Despite the resolution, Achilles and the tortoise still fascinate us, raising questions about motion, infinity, and reality. The barber paradox, sometimes called a more light-hearted twist on Russell's paradox, the barber paradox poses a simple scenario. There is a barber in a village who shaves all and only those men who do not shave themselves. The puzzle: who shaves the barber? If the barber shaves himself, he shouldn't, based on the rule that he only shaves those who don't shave themselves. If he doesn't shave himself, then he should, because the barber's job is to shave those men who don't do it on their own. This contradiction arises from the barber's dual role as both a potential client and the provider of the service. The paradox is really a disguised version of the self-reference trap. Can a set, or in this case, a person, apply its own rules to itself without contradiction? Like Russell's paradox, the solution typically involves realizing there's no consistent way to define this barber within a standard logical framework. Something has to give. Either the village's rule must be incomplete, or the scenario is simply impossible. The barber paradox invites us to think about how easily a neat-sounding premise can self-destruct if it loops back onto itself. It's a cautionary tale about the perils of universal definitions that inadvertently include themselves. The Sorites paradox. Take a single grain of sand. It's obviously not a heap. Add another grain, and it's still not a heap. Keep adding grains, one at a time. At what exact point do you cross the boundary from not a heap to a heap? The Sorites paradox, from the Greek word for heap, spotlights the problem of vague predicates, words like heap, tall, or bald, which lack a clear-cut boundary. If you say, one grain is not a heap, then by that logic, 2 grains aren't a heap, 3 grains aren't a heap, and so on. Step by step, you never find a magical transition moment. Yet at some point, we intuitively agree there is a heap of sand. The paradox reveals how everyday language can be slippery because of these fuzzy concepts. Philosophers debate whether to solve it by rejecting the idea that vague terms can be pinned down with precise cutoffs, or by insisting we can define boundaries, however arbitrary they may be. In everyday life, We often rely on context and common sense instead of rigid definitions. The Sorites paradox reminds us that language is often more about practical usage than about absolute lines, shining light on how we navigate uncertainty in daily thinking. The crocodile paradox. In an ancient puzzle, a crocodile snatches a child and promises to release the child if the parent correctly guesses what the crocodile will do next. If the parent guesses, "You will return my child," how should the crocodile respond? If the parent is correct, the crocodile must release the child, but then the parent's guess is indeed accurate. If the parent is incorrect and the crocodile keeps the child, that means the parent's guess was wrong. But if it was wrong, by the deal, the crocodile doesn't have to keep the child. This paradox forms a loop of logical confusion, similar to the liar paradox. It involves a self-referential prediction. The guess itself affects the crocodile's next action, which in turn affects the truth of the guess. Philosophically, it illustrates the complication of letting future actions hinge on statements about those actions. It also highlights how contract or promise-based logic can twist itself into knots if it's not carefully framed. Like many paradoxes, the crocodile paradox suggests certain statements can't be simply labeled true or false without contradiction. It's an age-old reminder that language, especially when referencing itself, can create cunning traps for our logical minds. The twin paradox. Rooted in Einstein's special relativity, the twin paradox goes like this. Suppose one twin rockets off into space at near light speed while the other stays on Earth. When the traveling twin returns, they find they've aged less than the twin who stayed behind. At first glance, it seems contradictory. Why can't the traveling twin view Earth as moving while they remain still, thus concluding the earthbound twin should be younger? The resolution lies in recognizing that the traveling twin's frame of reference is not inertial the whole time. They have to accelerate, turn around, and decelerate to come back. Special relativity's time dilation formulas apply differently when acceleration enters the picture. The earthbound twin remains in a single inertial frame, neglecting Earth's own accelerations for simplicity, whereas the traveling twin changes frames mid-journey. The paradox is mind-blowing because it contradicts our everyday assumption that time flows uniformly for everyone, everywhere. Instead, the experience of time can diverge significantly for observers moving at relativistic speeds. It underscores how motion and acceleration affect the passage of time. The twin paradox highlights the marvel of relativity. The fabric of space-time warps in ways that defy simple human intuition. Hilbert's Grand Hotel. Welcome to Hilbert's Grand Hotel, a legendary thought experiment illustrating the strange properties of infinite sets. Imagine a hotel with an infinite number of rooms, every one of them occupied. At first glance, you'd think it's full. But when a new guest arrives, the hotel manager simply moves the occupant of room 1 to room 2, room 2 to room 3, and so on, shifting each occupant into the next room number. This frees up room 1 for the new arrival, even though every room was already taken. The puzzle gets weirder. Even if infinitely many new guests arrive, the manager can move the occupant of room 1 to room 2, room 2 to room 4, room 3 to room 6, and so on, doubling each room number. Now all odd-numbered rooms become available, accommodating infinitely many new arrivals. Hilbert's Grand Hotel highlights how our intuition about full capacity fails for infinite sets. You can always shuffle an infinite set to make room for more elements, something unthinkable with finite collections. This thought experiment underpins the mathematical concept of different sizes or cardinalities of infinity. It's a heady reminder that at infinite scales, common sense must yield to the surprising logic of mathematics. The lottery paradox. Here's the scenario. In a fair lottery with millions of tickets, you can rationally believe any single ticket is almost certain to lose. Yet, you also know one ticket will win. So, believing ticket number 1 will lose, ticket number 2 will lose, and so on, for every ticket, conflicts with believing some ticket will win, even though all seem logically justified. This paradox challenges how we handle reasonable belief. If you say each ticket is likely a loser, you end up believing there can't be a winner, an obviously false conclusion. But if you refuse to say each ticket is a likely loser, you deny a perfectly sensible inference from probability. Philosophers and logicians use this paradox to examine the standards for justification in everyday reasoning. Should we call it knowledge if something is highly probable but not guaranteed? The lottery paradox suggests that standard definitions of justified belief might break down in large-scale probabilistic scenarios. In practical terms, it reminds us that while each event might be incredibly unlikely, collectively, one outcome must happen. It's not purely a numbers game, but also about how we define rational belief in the face of uncertainty, a subtle distinction often overlooked in casual, probabilistic thinking. The two envelopes paradox. You're given two envelopes, each containing some amount of money, but you don't know how much. One envelope has exactly twice as much as the other. You pick one envelope at random. At this point, you think, if I switch, I could double my money if this envelope is the lower one, or halve it if this is the higher one. Mathematically, it might seem the expected value of switching is the same as sticking. Yet, a trick in reasoning suggests you have a 50% chance to double your money and a 50% chance to have it. So you might be tempted to believe switching has a net positive expectation. But that conclusion is misleading. The confusion arises from incorrectly assigning probabilities to this envelope has X, the other has 2X, or this envelope has 2X, the other has X, without anchoring it to the actual amounts. When you consider the amounts more carefully, you see the symmetrical nature of the situation. The two envelopes paradox demonstrates the importance of avoiding naive probability assumptions, especially around unknown quantities. It's a classic example of how easy it is to fool ourselves with incomplete references to monetary amounts and chances, and it continues to spark debates among philosophers and mathematicians. The missing dollar riddle. A classic mind teaser. 3 guests pay $30 for a hotel room, $10 each. Later, the desk clerk realizes the room should have cost only $25, so he gives $5 to the bellhop to return. The bellhop keeps $2 and gives $1 back to each guest, so they each paid $9, totaling $27. Adding the bellhop's kept $2 gives $29. Where's the missing dollar? The confusion arises because we shouldn't add the $2 kept by the bellhop to the $27 the guests paid. That $27 already includes the $2. The correct math is the guests paid $27 total. $25 went to the hotel, and $2 stayed with the bellhop. There's no missing dollar. The riddle demonstrates how a misleading line of arithmetic can create an apparent paradox. By tacking on the $2 to $27, you're double counting. It's akin to saying they paid $27, of which $25 is for the room plus $2 for the bellhop. Summing $27, the guest's total outlay, and $2 is the error. This puzzle is a fun illustration of how easy it is to get tripped up by faulty grouping of expenses. It highlights that we must carefully track what each figure represents. Otherwise, we conjure a paradox where none actually exists. Russell's paradox. Imagine a large library that keeps track of all catalogs listing books. Now, imagine there's a special catalog that lists all catalogs that do not list themselves. The question is, does this special catalog list itself or not? If it does, then by definition, it can't. If it doesn't, then by definition, it must. British philosopher and mathematician Bertrand Russell formulated a set theory version of this puzzle in the early 1900s. At its heart, Russell's paradox shows a fundamental contradiction if we allow sets that can contain themselves. For instance, consider the set of all sets that do not contain themselves. Does that set contain itself? If it does, it shouldn't. If it doesn't, it should. This discovery shook the foundations of mathematics and logic, prompting the development of more rigorous axiomatic set theories that avoid such self-swallowing definitions. It's a stark demonstration of how an apparently logical system can break down if it allows for too much self-reference. Russell's paradox is sometimes used as an analogy for everyday situations where circular definitions cause confusion. Ultimately, it reminds us that infinite or self-referential constructs can lead to jarring contradictions, forcing us to be cautious about what we allow in our definitions. Schrödinger's cat. Picture a sealed box containing a cat, a radioactive atom, and a mechanism that will release poison if the atom decays. According to quantum mechanics, before the box is opened, the atom state can be described as a superposition of decayed and not decayed. Therefore, the cat can be thought of as both alive and dead at the same time until an observer opens the box. Austrian physicist Erwin Schrödinger intended this thought experiment as a critique of certain interpretations of quantum theory, highlighting how bizarre it sounds to apply quantum principles to everyday objects. The paradox underscores the role of the observer in determining the state of a quantum system. Does measurement physically force the system to choose a specific outcome? Or is the cat truly alive or dead the whole time, and quantum mechanics is just incomplete in describing it? This puzzle spurred debates about the nature of reality, prompting ideas like the many worlds interpretation, where the cat is alive in one branch of the universe and dead in another. Ultimately, Schrödinger's cat demonstrates how quantum weirdness clashes with our common sense world, challenging us to rethink what it means for something to exist in a definite state. Zeno's arrow paradox. Zeno of Elea proposed another conundrum. An arrow in flight is, at any given instant, at rest in a particular position. If at each instant the arrow isn't moving, how does it ever traverse a distance? Summing up all those instants would suggest the arrow never moves at all. The paradox seems absurd because we observe arrows, or any objects, traveling from point A to point B all the time. Modern calculus resolves this paradox by considering infinite sums in a way that yields a finite result. When we dissect the arrow's journey into tiny time slices, each slice is indeed a snapshot where the arrow occupies a particular position. Yet the arrow's velocity is not determined by looking at a single instant alone. It's the relationship between distance and time over an interval. By integrating, summing those infinitesimal distances over infinitesimal times, mathematics shows the arrow travels a finite distance in finite time. The paradox arises from mixing up motion in an interval with the position at a single, frozen moment. Nonetheless, Zeno's puzzle still resonates with anyone intrigued by how continuous motion can be broken into infinitely many still frames. If every frame is no movement, how does motion emerge at all? Philosophically, this begs the question of whether time is continuous or discrete, and how the concept of motion is truly defined. Banach-Tarski paradox. Imagine taking a solid sphere, like a basketball, cutting it up into a finite number of pieces, then reassembling those pieces, without stretching or changing their shape, into two spheres identical to the original. That's the mind-blowing Banach-Tarski paradox. It defies our normal sense of volume and matter. The trick lies in the fact that these pieces are infinitely complicated, relying on sets of points so wildly scattered that they're impossible to visualize. This paradox emerges from the axiom of choice in set theory, which allows for the selection of points in sets in ways that intuition can't grasp. In standard three-dimensional space, with standard mathematics, it's logically consistent that you can partition a sphere into a few clever chunks and rearrange them to get two full spheres of the same size. That implies a kind of infinite mass creation. But the pieces aren't ordinary shapes. Each piece is non-measurable in terms of volume. While it doesn't threaten physical conservation laws in actual physics, we can't literally do this in real life. Banach-Tarski shows how pure mathematics can lead to results that seem impossible. It's a testament to the power, and sometimes the strangeness, of abstract logical assumptions and infinite sets. The unexpected hanging paradox. A judge tells a condemned prisoner he'll be hanged at noon on one weekday in the following week, and it will be a surprise. The prisoner reasons, it can't happen on Friday, because by Thursday night, if I haven't been hanged, Friday wouldn't be a surprise, so I can eliminate Friday. Now it can't be Thursday either, because if I make it to Wednesday night without being hanged, then Thursday would be the last possible day, hence not a surprise. By this backward logic, I can eliminate every day, so I won't be hanged at all. Feeling confident, the prisoner is stunned when they come for him on, say, a Wednesday, defying his proof. The paradox arises from mixing knowledge with unknown timing. By using backward induction, the prisoner assumes that they'll have perfect foresight by the time each remaining day arrives. But the actual element of surprise is that the prisoner's assumptions fail. The prisoner believes the event is logically impossible, so they stop expecting it. which restores the element of surprise. Similar to the surprise examination paradox, it challenges how we treat knowledge of future events and how that knowledge might invalidate the event's unpredictability until it doesn't. The bald man paradox, a close cousin to the standard Sorites paradox. This version asks, how many hairs must a man lose before he's considered bald? Start with someone with a full head of hair. If losing one hair doesn't instantly turn him bald, then losing one more probably won't either, and so forth. Taken step by step, no single hair's loss would seem to mark the threshold moment. Yet eventually, we do say the man is bald. The puzzle underscores the continuum between having hair and having none, and our difficulty in assigning sharp boundaries to vague concepts. Philosophers have tried to resolve it with fuzzy logic, which allows for truth values that aren't strictly yes or no, or by adopting arbitrary cutoffs, such as a specific hair count. However, any cutoff remains artificial and doesn't align perfectly with our intuitive sense of baldness. This scenario shows that while these paradoxes seem playful, they reflect real-world challenges. Medical diagnoses, legal definitions, and everyday judgments often rely on vague terms. Sorites type paradoxes demonstrate that language is an imprecise tool. Whether it's grains in a heap or hairs on a head, the puzzle remains. At which precise point do we really say, this is something else now? The observer's paradox. Different from the quantum observer effect, the observer's paradox in sociolinguistics points out that by observing a phenomenon, you often alter it. In studying how people naturally speak, for example, the mere presence of recording equipment or an interviewer can cause people to speak differently, more carefully, more formally, or just unnaturally. The very act of observation changes the behavior being observed, making it hard to capture genuine, unselfconscious language. This phenomenon isn't limited to linguistics. Psychologists face it in experiments where participants might be influenced by the knowledge they're being studied, the Hawthorne effect. It also appears in fields like anthropology, where observers try to minimize their impact on the cultures they study, but inevitably shape interactions. The observer's paradox forces researchers to devise ingenious methods, like covert recordings or extended immersion in a community, to reduce participants' self-consciousness. It raises ethical questions about privacy and consent, but remains a valuable concept. Knowledge gathering can never be 100% neutral. By highlighting how observation contaminates data, the paradox serves as a reminder that we cannot always separate observer from observed. In everyday terms, think of how you tidy up your house more thoroughly because you know guests or an inspector are coming to see it. Galileo's paradox. Galileo observes something curious about the set of natural numbers 1, 2, 3, and the set of squares 1, 4, 9. Logically, it seems there are fewer squares than natural numbers because most numbers aren't perfect squares. Yet, we can pair each natural number n with its square n2, creating a one-to-one correspondence. This implies the two sets are the same size, infinite, yet equally infinite. Galileo's paradox reveals the counterintuitive nature of comparing infinite sets. Unlike finite sets, where one set having fewer elements obviously makes it smaller, infinite sets defy that simple logic. Later, Georg Cantor formalized this understanding with the concept of cardinality, showing that sets can be countably infinite or uncountably infinite, among other distinctions. The mind-bending result is that while intuition rebels against equating all numbers with just the squares, mathematically, they are the same in terms of cardinality. This paradox forced thinkers to refine their approach to infinity. We can't just rely on common sense when dealing with unbounded sets. Galileo's insight was one of the early stepping stones toward a more rigorous understanding of infinity, reminding us that reality at the infinite scale can be deeply strange. The card paradox. Imagine a simple card inscribed on both sides. Side A says, the statement on side B is true, while side B says, the statement on side A is false. Side A's claim implies side B's statement is correct, yet side B's statement insists side A's statement is false, which means side A's statement would be incorrect about side B being true. If side B is true, then side A is false. And if side A is false, then side B is false about side A being false. Round and round it goes. This puzzle is like the liar paradox, but uses two statements referencing each other rather than one statement referencing itself. By splitting the contradiction across two sides, it momentarily looks more approachable, but the logical knot remains. The paradox underscores how referencing the truth value of another statement, especially in a loop, can generate contradictions. Similar setups appear in logic puzzles, from two guards who always lie or always tell the truth, to multi-person riddles where each participant comments on the honesty of the others. At its core, the card paradox highlights that the concept of truth becomes tangled when statements define each other's validity, demonstrating the pitfalls of self-referential or mutually referential language. The Fermi paradox. Named after the physicist Enrico Fermi, this paradox asks a deceptively simple question. Where is everybody? Given the vast number of stars in our galaxy and the near certainty of countless Earth-like planets, our calculations suggest that extraterrestrial civilizations should be plentiful, yet we haven't encountered definitive evidence of alien life, nor have we observed any unmistakable signs like radio transmissions or megastructures. So why the silence? Possible explanations abound. Maybe intelligent life is rarer than we think. Perhaps advanced civilizations are short-lived, wiping themselves out before they can explore or broadcast. Others suggest that aliens are out there but deliberately avoiding us under something like the Prime Directive, or they're using communication methods beyond our understanding. There's also the notion that we're in a cosmic backwater, too far off the beaten path to notice. The Fermi paradox cuts to the heart of our assumptions about life, technology, and the natural drive to explore. If the universe teems with life, why are we seemingly alone? This question teases us, urging deeper astronomical searches while also provoking philosophical reflection. Maybe the silence tells us something about our own future, or about the delicate odds of life evolving to our level at all. Simpson's paradox. Simpson's paradox reveals that trends visible in different groups of data can reverse when those groups are combined. Imagine a medication's effectiveness measured in two separate trials, Trial A and Trial B. The drug seems to outperform a placebo in each trial individually. But when you pool the data, it suddenly looks like the placebo did better overall. At first glance, this reversal seems impossible. How can you beat the placebo in every subgroup but lose once all groups merge? The key lies in how the data is distributed. One group might be larger or have different characteristics that skew the combined results. The paradox highlights that simple comparisons can be misleading without context. Real-world examples pop up everywhere, from medical research to sports stats, and even political polling. Suppose a baseball player has a higher batting average against left-handed pitchers and right-handed pitchers separately, but when total hits are compared across all at bats, they end up with a lower overall average. Simpson's paradox is a cautionary tale in statistics. Always pay attention to potential lurking variables and the structure of your data. It's a sobering reminder that the numbers can be more subtle than they first appear. Quine's paradox. Quine's paradox presents a self-referential puzzle similar to the liar, but structured around a phrase that describes itself. It can be phrased like this: yields falsehood when preceded by its quotation, yields falsehood when preceded by its quotation. In other words, you take the statement, quote it, and then attach it to itself, producing a confusing loop of truth values. This paradox is named after philosopher Willard Van Orman Quine, who explored how statements could reference themselves in the language of logic. The essence: you have a phrase that instructs you to do something with that very phrase, creating a swirl of self-reference. If the statement is true, it leads to a contradiction. If it's false, you run into the same problem. Quine's paradox stands as a reminder that language can be twisted into forms that defy standard truth conditions. Much like Russell's paradox and the Barber paradox, it forced logicians to carefully consider how to construct a formal language that avoids self-referential pitfalls. While it might feel esoteric, it's a prime example of how easily language can sabotage itself, requiring us to craft rules that limit self-reference, or else embrace the paradoxical results. Moore's paradox. Philosopher G.E. Moore highlighted a curious contradiction in everyday speech. Consider the statement, "It's raining, but I don't believe it's raining." On the face of it, there's nothing logically inconsistent. Rain could be falling while the speaker remains unaware or in denial. Yet saying this aloud sounds absurd. Once you declare, "It's raining," you're effectively showing that you believe it, or at least assert it. Why is it so strange? Because in normal conversation, asserting something implies you believe it. The second part contradicts the commitment implied by the first part, but it's not a contradiction about facts, rather a clash between the propositional content, "It's raining," and the speaker's mental state, "I don't believe it." Moore's paradox illustrates that language carries pragmatic meaning beyond raw truth values. We reveal our beliefs, or at least our stance, when we make statements. Therefore, pairing X is true with "I don't believe X" disrupts the usual coordination between statement and belief. This phenomenon raises questions about the nature of belief, assertion, and what it means to communicate truth claims. It points out that logic alone can't capture the entire social dimension of conversation, where beliefs and statements are deeply intertwined. The Gettier problem. The Gettier problem isn't always called a paradox, but it functions like one in epistemology. Traditionally, philosophers described knowledge as justified true belief. If you believe something, have good reasons, justification for it, and it's true, then you supposedly know it. Edmund Gettier's 1963 paper presented scenarios where someone seems to have justified true belief. But we're reluctant to call it genuine knowledge. One classic example. Suppose Smith had strong evidence that Jones owns a Ford and that Jones is in Barcelona. So Smith concludes either Jones owns a Ford or Brown is in Boston. A logically valid proposition. Coincidentally, Jones doesn't own a Ford, but by pure chance, Brown is in Boston, making Smith's statement true. Smith is justified through misleading evidence, and the statement is true. Yet it feels wrong to say Smith actually knows it. The puzzle unsettles a centuries-old definition of knowledge. It reveals that having a justified true belief might still rely on a stroke of luck to be correct, which we hesitate to label as real knowledge. Philosophers have proposed various additions, like no false lemmas or reliability conditions, to patch the definition. The Gettier problem persists, challenging us to pin down precisely what separates genuine knowledge from mere fortunate belief. Newcomb's paradox. You encounter a peculiar game. Two boxes sit in front of you. Box A is transparent and visibly contains $1,000. Box B is opaque, and it might contain $1,000 or nothing at all. A predictor, claimed to be extremely accurate, has already made a prediction about your choice. If the predictor foresaw you'd pick only box B, it put $1,000 inside. If it foresaw you'd pick both boxes, it left box B empty. Now you get to choose. Do you grab both boxes or just box B? A dominance argument says you should take both. After all, the predictor's choice is already made. You can't change what's inside box B now. So why pass up the guaranteed $1,000 in box A? Conversely, a maximize expected value argument says you should pick only box B because the predictor is so accurate that your choice strongly correlates with what's in box B. Opting for just box B usually yields $1 million, while grabbing both typically leaves box B empty. There's no consensus resolution. Some people emphasize free will and logic. Others highlight correlation and rational expectation. Newcomb's paradox remains one of the most discussed puzzles in decision theory, exposing rifts between rational choice and predictive determinism. Bertrand's box paradox. You have 3 boxes. Box 1, 2 gold coins. Box 2, 2 silver coins. Box 3, 1 gold and 1 silver coin. A box is chosen at random, and you draw 1 coin from it at random. The coin you draw is gold. What's the probability that the other coin in that same box is also gold? Many jump to 1/2, reasoning that either you pick the 2 gold coins box or the 1 gold, 1 silver box. But the correct answer is 2/3. Here's why. There are 3 gold coins total across the 3 boxes. 2 are in box 1, and 1 is in box 3. If you pull a gold coin, it's more likely you chose one of the 2 gold coins in box 1 than the single gold coin in box 3. Hence, The probability that you're in the 2 gold box is 2 out of 3 possible gold coin scenarios. This paradox demonstrates how intuitive, equally likely assumptions can be misleading when dealing with probability. It's akin to the Monty Hall problem, famous for confounding people's sense of odds. Bertrand's box paradox nudges us to carefully count all ways an event could happen, rather than rely on quick guesses about even splits. The boy or girl paradox, sometimes called the two-child paradox, it goes like this. You meet someone who has 2 children, and you know at least one is a boy. What's the probability the other child is a girl? People often jump to 1/2, believing the second child's gender is unaffected. But if you dig deeper, the possible combinations for 2 children, boy, 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 girl, girl, boy, need careful counting. The trick, if you only know there's at least one boy, that excludes girl, girl. But does one boy refer to a boy born on Tuesday, or simply a boy in general? Different formulations shift probabilities. In the standard version, boy-girl and girl-boy are considered 2 distinct outcomes. So the probabilities for the other child is a girl come out as 2-3, because boy-boy, boy-girl, and girl-boy are all possible. And in 2 of those 3, there is a girl. Yet it can also be 1/2 if you interpret the statement differently, like you specifically met the older boy. The paradox highlights how subtle changes in how information is presented can swing the probabilities drastically. It's a reminder that we must define the conditions precisely when reasoning about chance, or risk being perplexed by contradictory answers. The Monty Hall problem. Based on a classic American game show, you face 3 doors. Behind one is a fabulous prize, and behind the other 2 are worthless goats. You pick one door, but before it's opened, the host, who knows where the prize is, opens one of the 2 remaining doors, always revealing a goat. Then you're asked, do you stick with your original door or switch to the other unopened door? Your gut might say it's a 50-50 toss-up, but the math says switching doubles your odds of winning. When you first choose, there's a 1/3 chance you pick the prize door and a 2/3 chance it's behind one of the other 2. By opening a goat door, the host effectively funnels that 2/3 probability onto the remaining unopened door. Why is it so mind-twisting? Because it feels like the situation resets after one goat is revealed, leaving 2 doors and intuitively a 50-50 chance. But the key is the host's knowledge and behavior. He will never open the door with the prize. That selective reveal shifts the probability in favor of the door you didn't pick. This puzzle famously confounds even seasoned mathematicians, demonstrating how our intuition about probability can mislead us. The dictionary paradox. Open a dictionary and you'll find a network of words defining other words. But if every word is defined by more words, and those words are similarly defined by more words, how do we ever reach a bedrock of meaning? This is sometimes called the dictionary paradox or the definition paradox. In principle, language is circular. Apple might be defined as a type of fruit, which is defined as a seed-bearing structure, which might be explained in other terms. And eventually, you loop back through synonyms and rephrasings. Where does it end? Some argue it's resolved because language ultimately rests on shared experiences and observations. We point to a real apple and say, "That's an apple." Over time, we build up a communal understanding. Yet conceptually, we see that no single definition can ever fully stand on its own if it relies on more words that themselves need definitions. A dictionary is more like a labyrinth than a linear chain of meaning. Philosophically, it mirrors how knowledge often feels self-referential. Still, in practical use, we navigate the web of definitions effectively because we bring prior context to each explanation. The dictionary paradox reveals the subtle interplay between language, experience, and understanding. The reverse drain paradox, also known as the bathtub vortex paradox. Imagine water swirling down the drain in a clockwise fashion in the northern hemisphere. Some might claim it should swirl counterclockwise because of Earth's rotation, and they're confused when it doesn't. In truth, the Coriolis force, due to Earth's rotation, is extremely weak on such a small scale. Bathtub or sink drains. The direction of the swirl is usually determined by the initial motion of the water and the geometry of the container. Why is it called a paradox? Because many people are taught the Earth's spin dictates swirl directions in opposite hemispheres. Yet real-life observations vary. The confusion arises from mixing a large-scale phenomenon, like hurricanes turning counterclockwise in the northern hemisphere, with a small-scale drain. Hurricanes cover hundreds of miles, enough for the Coriolis effect to accumulate and shape their rotation. A tiny drain doesn't provide that opportunity, so there's no genuine contradiction, just a misconception that Earth's rotation must always dictate the swirl. The paradox highlights how an effect that's significant on a planetary scale can be negligible in everyday situations. Our quest to see Earth's rotation in small draining basins runs headlong into the realities of fluid dynamics and local conditions. Aristotle's wheel paradox. Picture a wheel with two circular edges of different diameters, like a smaller circle attached to a larger one on the same axle. When it rolls on a flat surface without slipping, each full rotation of the axle would, theoretically, have both circles trace a circumference length distance. But the larger circle has a bigger circumference than the smaller circle. How can both the big circle and the small circle travel exactly one circumference's distance in a single rotation? At first, it seems contradictory. How does the smaller circle keep up with the bigger one? The paradox is resolved by focusing on contact points and the path traced by each circle's outer edge. When the smaller circle is in contact with the ground, it indeed traces a distance equal to its own circumference per rotation. Simultaneously, the larger circle's contact point moves along a path matching its circumference. Aristotle's wheel shows how intuitive distance traveled can break down when different parts of a single object move differently, even in the same rotation. Modern mathematics clarifies that each circle has its own rolling constraints. This paradox is another demonstration that analyzing motion through geometry can lead to surprising and counterintuitive results. Bertrand's paradox, geometry. Bertrand's paradox in geometry is about randomly choosing a chord in a circle and figuring out the probability that the chord is longer than the circle's side length of an inscribed equilateral triangle. The surprising twist: the answer depends heavily on how you define random. Different methods yield different probabilities: 1/3, 1.5, or 1/4, illustrating that random chord is ambiguous. For instance, you could select two random points on the circumference uniformly, forming a chord. Or you might pick a random radius and then pick a random point along that radius as the midpoint of your chord. Another method is picking a random midpoint anywhere within the circle's area. Each approach seems reasonable, yet they produce distinct results because the underlying probability distributions differ. This paradox underscores a core principle in probability theory. Random is not always well defined without explicit clarification of the sampling process. The geometry-based puzzle forced mathematicians to be more precise about probability measures in continuous spaces. Bertrand's paradox resonates beyond geometry. It reminds us that in any experiment or model, how we choose a random process can fundamentally alter outcomes. It's a cautionary tale that the phrasing of a problem can shape its solution. Hempel's paradox, Raven paradox. If you hypothesize all ravens are black, then any observation of a black raven supports your hypothesis. But what about seeing a green apple? According to some lines of logic, if all ravens are black, the contrapositive is, if something is not black, then it is not a raven. Observing a green apple, not black, not a raven, seems to confirm the contrapositive, thus confirming all ravens are black. Intuitively, that's absurd. How does a green apple tell us anything about ravens? Welcome to Hempel's paradox. It arises from the logical equivalence between a statement, all ravens are black, and its contrapositive, all non-black things are non-ravens. While they're logically the same, we feel like they're not equally informative. Philosophers deal with this by discussing context and relevance. Viewing a random green apple in the fruit bowl doesn't genuinely address the question of raven color. Some point out that an observation must be relevant to the hypothesis you're testing. Others use Bayesian reasoning to illustrate that while technically the green apple might incrementally confirm all ravens are black, the effect is so minuscule as to be practically meaningless. Hempel's paradox highlights the gulf between formal logic and our intuitive sense of empirical confirmation. St. Petersburg paradox. Imagine a game where you toss a fair coin until it lands heads. The payout is $2 if heads appears on the first toss, $4 if it appears on the second toss, $8 on the third, and so on, doubling each time. In theory, the expected value of this game is infinite. Every extra toss extends the possibility of doubling the payout enough to offset the diminishing probability. But in real life, almost nobody would pay a massive entrance fee to play this game. Why? Because although the mathematical expectation is infinite, the probability of very high payouts is minuscule. Most times, you get a fairly modest return. Real-life behavior also factors in risk aversion and the diminishing utility of large sums of money. The paradox, first described by Daniel Bernoulli, shows that raw expected value might not capture how people actually evaluate potential gains. Bernoulli introduced the concept of utility, suggesting we value money logarithmically. An extra $1,000 means more to someone with $0 than to someone with millions. This is often called the diminishing marginal utility of wealth. The St. Petersburg paradox thus helped shape modern economic theory, especially around decision-making under uncertainty and risk aversion. The bootstrap paradox. A time travel conundrum, the bootstrap paradox, sometimes called the ontological paradox, involves an object or piece of information that's passed from the future back into the past, creating a loop with no clear origin. Suppose you find a copy of Shakespeare's Hamlet that traveled from the future to the past, and you publish it under your own name, leading eventually to the future publication you originally received. Where did Hamlet really come from? It appears out of nowhere, with no true author. The paradox raises questions about causality and creation. Is it logically possible for something to come into existence purely through time travel? And if so, does that object have a beginning? Or is it stuck in a perpetual closed time-like curve? In science fiction, these scenarios highlight the bizarre implications of time loops. From the perspective of classical causality, it seems impossible for something to have no origin. Yet certain theoretical models of space-time suggest such loops might be mathematically permissible, if not physically probable. The bootstrap paradox hovers over the same territory as the grandfather paradox, pushing us to reflect on whether time travel can exist without unraveling the very fabric of cause and effect. The predestination paradox, often encountered in time travel fiction, the predestination paradox refers to events that appear inevitable because future actions cause past events, which in turn trigger those same future actions. Imagine you travel back in time to prevent a disaster, only to inadvertently cause it by your interventions. Your attempt to rewrite history is actually part of the timeline's established chain of events, making the outcome predestined. This puzzle is sometimes tied to the idea of a self-consistent timeline. If time travel is possible, maybe the universe prevents paradoxes by ensuring everything lines up so the timeline doesn't change. You can't kill your own grandfather because something will inevitably thwart you. Maybe you fail or accidentally cause your grandfather to meet your grandmother sooner. The predestination paradox underscores the tension between free will and determinism in a universe where time loops exist. Are you truly free if your future trip to the past has already shaped present-day reality? Or are you just acting out a script that's already written? It's a profound philosophical question wrapped in a sci-fi scenario. The paradox challenges our intuitive sense that the future is open and the past is fixed, suggesting that maybe both are fixed if time can loop back on itself. Grelling-Nelson paradox. Consider the word autological, meaning a word that describes itself. For example, short is arguably autological if you think the word short is itself short in length. Meanwhile, long would be heterological if the word long is not long in length. Now, take the word heterological, which means not describing itself. If heterological does describe itself, then it shouldn't. If it doesn't describe itself, then by definition it does. This is the core of the Grelling-Nelson paradox, a clever linguistic twist akin to the liar paradox. It exploits self-reference in definitions, revealing that language can become tangled when words refer to their own properties. If a word's meaning is about whether it applies to itself, logic can loop around in circles. One attempt at resolution is to argue that such self-referential terms are simply ill-defined. Another is to refine set theory or language rules to exclude pathological cases. Yet, like many paradoxes, it underscores how easily language can defy tidy logic. Beyond a playful curiosity, the Grelling-Nelson paradox highlights the potential for contradiction whenever definitions loop back onto themselves. An enduring reminder of the limits of purely self-referential descriptions. Menno's paradox, originally posed by Plato through the character Menno. This paradox questions how anyone can ever learn something truly new. The argument goes, if you know something already, you don't need to learn it. Yet if you don't know it, how will you recognize it or even know what to look for? Either you already have knowledge or you can't acquire it. At face value, it suggests a self-defeating loop. Searching for knowledge might be impossible because you either already possess that knowledge or you have no way of verifying when you found it. Plato's own response introduces the concept of recollection, suggesting perhaps the soul already knows everything from before birth, and learning is just remembering. Later philosophers interpret it differently, seeing the paradox as highlighting how we refine hypotheses by trial, error, and partial understanding, eventually pinpointing truths. In modern terms, think of it as the bootstrap problem in AI, or the puzzle of forming new scientific theories. If we only have old concepts, how do we generate genuinely novel ideas? Menno's paradox reminds us that learning isn't always a straightforward process. Sometimes you must grope in the dark, guided by intuition and partial clues, until something clicks into place and new knowledge forms. Olber's paradox. Look up at the night sky. It's dark. But if the universe has infinitely many stars scattered endlessly in all directions, shouldn't we see a bright sky no matter where we look? That's Olber's paradox, named after the 19th century astronomer Heinrich Wilhelm Olbers. If space were infinite, static, and eternal, every line of sight should end at a star, making the sky glow as bright as the sun's surface. Yet, we experience night as mostly dark, studded with distant stars. How come? Modern cosmology offers several explanations. One is the finite age of the universe. Not all light has had time to reach us yet, because the universe is only about 13.8 billion years old. Another is cosmic expansion. As the universe stretches, light from distant galaxies gets redshifted, diluted, and shifted out of visible range. Additionally, stars aren't immortal. They have lifespans, so the distribution of luminous stars isn't uniform through infinite time. Olber's paradox was an early hint that something about an infinite, unchanging universe didn't add up. Today, its resolution underscores the Big Bang model, cosmic expansion, and the idea that our visible universe has boundaries in both space and time. It's a striking reminder that even a simple nighttime observation can hold profound cosmological implications. The Sleeping Beauty Problem. The Sleeping Beauty problem goes like this. Sleeping Beauty is put to sleep on Sunday. A fair coin toss decides what happens next. If heads, she's awakened once, Monday. If tails, she's awakened Monday, and her memory is wiped and awakened again on Tuesday. though she remembers none of it. After she wakes up and sees it's someday, what's her probability the coin landed heads? One perspective says it's a 1/5, because the coin toss is fair. Why complicate it? Another perspective, often called the thirder position, says the correct answer is wall on 3, because there are 3 equally likely awakening scenarios: heads Monday, tails Monday, and tails Tuesday. In 2 out of 3, the coin was tails. The controversy hinges on how we treat memory erasure and repeated awakenings as separate events. Is there a difference between the coin has a 50-50 chance and Sleeping Beauty's viewpoint across multiple awakenings? The puzzle reveals how probability can shift when you factor in observer moments. No universal consensus exists, though many side with the thirder argument. The Sleeping Beauty problem underscores that probability can be context-sensitive. How we measure likelihood depends on how we count distinct instances or perspectives in scenarios involving uncertainty and repeated experiences, the friendship paradox. It might surprise you to learn that on average, your friends likely have more friends than you do. That's the friendship paradox. It arises from a quirk of network theory. Highly connected people appear in more friendships, so they're more likely to be someone's friend. Think of it this way. If you have 10 friends, but there's another person in your circle with 50 friends, that popular individual shows up in many people's friend lists, skewing the average for others. More formally, if you pick a random friendship link in a social network, it's likely to connect to a person with a higher than average number of connections. As a result, your friends, on average, tend to be more socially connected than you. This paradox extends beyond social relationships. The same principle applies to citation networks in academia, where the papers you cite, on average, are more highly cited than your own. Or consider social media. Your Twitter or Instagram feed might make you feel your life is dull because you see content from people who post or connect more often. At its heart, the friendship paradox reflects how sample bias skews our perspective. It's a reminder that average experiences can differ wildly from one's personal vantage point, the paradox of tolerance. Philosopher Karl Popper famously argued that unlimited tolerance might lead to the disappearance of tolerance itself. If a society extends tolerance to intolerant ideologies that use violence or suppression, those ideologies may eventually seize power and destroy the very principle of tolerance that allowed them in. This is the paradox of tolerance. Superficially, it's contradictory to say we should not tolerate the intolerant, because tolerance is about accepting differences. Yet if a group openly advocates eradicating or oppressing others, tolerating that stance can undermine the freedom of the broader community. Popper's solution suggests a limit to tolerance. We tolerate everything except calls for violent intolerance. The paradox highlights the delicate balance between freedom of expression and protecting a society's foundational values. Where do we draw the line between legitimate dissent and dangerous extremism? This question resonates in debates over hate speech, extremist propaganda, or the role of free speech on social media. Ultimately, the paradox of tolerance reminds us that tolerance isn't a blank check for destructive ideologies. In a truly open society, paradoxically, some boundaries must exist to preserve the environment in which free inquiry and mutual respect can flourish. The chicken or the egg paradox, a timeless riddle. Which came first, the chicken or the egg? From a biological standpoint, the question seems unsolvable if you assume a chicken has to hatch from a chicken egg, and such an egg must be laid by a chicken, which in turn hatched from an egg. The cycle appears endless. Evolutionary biology offers a resolution. The chicken we recognize today is the result of gradual genetic changes in chicken-like ancestors. At some point, a bird, almost a chicken, laid an egg containing a slight genetic mutation that made the offspring a proper chicken. In that sense, the egg came first, laid by a proto-chicken. That egg carried the final mutations needed to classify the hatchling as a modern chicken. Philosophically, the paradox is less about biology and more about infinite regress and definitions. If we define chicken egg as an egg laid by a chicken, you might say the chicken came first. If we define it as an egg that hatches into a chicken, then the egg was first. While science typically sides with the egg in evolutionary terms, the puzzle remains a charming illustration of how definitions and perspectives can tangle up the simplest questions. Immovable object versus unstoppable force. The classic confrontation. An unstoppable force meets an immovable object. Which one wins? By definition, an unstoppable force can't be halted by anything. An immovable object can't be shifted by anything. If they collide, we get a paradox. The contradiction arises because we're positing two absolute, all-encompassing qualities, complete inertia and infinite momentum, in the same universe. In realistic physics, there's no such thing as infinite mass or infinite energy, so the setup is impossible. But conceptually, we're forced into a logic puzzle. If the object truly cannot move, and the force truly cannot stop, neither can yield. Many argue the puzzle is unresolvable because it's self-contradictory. Both states can't coexist. Another approach is to reframe it. Maybe unstoppable means there's no external force strong enough to stop it. But if an immovable object is also not an external force, the unstoppable force might just pass by or interact differently. Alternatively, the collision could cause reality to break or never happen in the first place. Ultimately, the paradox highlights the folly of applying infinite, absolute notions in a single scenario. It's an epic-sounding puzzle that reminds us how extremes in logic can clash irreconcilably. The trolley problem. You see a runaway trolley heading toward 5 people tied to the tracks. You have the power to flip a switch to divert it onto another track, where it will only kill one person. Do you flip the switch? This is the classic trolley problem in ethics. Most people's gut reaction is to flip the switch, sacrificing one to save 5, a utilitarian stance. But then there's a twist. A second scenario where you can push a large man off a bridge to stop the trolley and save the same 5. Many become hesitant, seeing a moral difference between indirectly flipping a switch and directly causing someone's death by pushing them. The paradox exposes the complexity of moral intuitions. Should we judge actions purely by outcomes, killing fewer people, or factor in the manner and intention behind the act? Deontological views emphasize rules like don't kill, while utilitarian views stress maximizing overall well-being. Over decades, philosophers have spun countless variations. like whether the person on the single track is a loved one or if you're forced to choose at gunpoint. The trolley problem shows how moral instincts can shift dramatically when we tweak context, challenging simple formulas for right and wrong. The EPR paradox. Einstein-Podolsky-Rosen. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen proposed a thought experiment to illustrate what they saw as a completeness problem in quantum mechanics. They considered two particles that interact and then move apart, but remain entangled. Measuring a property, like momentum or position, on one instantly seems to affect the state of the other, no matter how far apart they are. What Einstein dubbed spooky action at a distance. Einstein believed the theory was incomplete, suggesting there must be hidden variables determining each particle's outcome. However, experiments starting in the 1970s, notably John Bell's work, consistently show that quantum mechanics predictions hold up. Entangled particles exhibit correlations exceeding any possible local hidden variable explanation. This phenomenon unsettles classical notions of locality, where no influence travels faster than light. While it doesn't allow for direct, faster-than-light communication, it does mean quantum events remain fundamentally probabilistic and correlated in ways classical physics can't mimic. The EPR paradox remains a central puzzle in interpreting quantum theory. Does it challenge realism, locality, or both? Different interpretations, like the many worlds view or Bohmian mechanics, offer different answers. But at its core, the paradox reveals how quantum entanglement defies our common sense expectations about separate objects and independent properties. No true Scotsman. The no true Scotsman paradox, or fallacy, arises when someone redefines a group in order to exclude counterexamples that would otherwise disprove a sweeping claim. Picture someone saying, "No Scotsman puts sugar on his porridge." If you point out a friend from Scotland who loves sugar in porridge, they retort, "Well, no true Scotsman would do that." At first glance, it seems like a neat rhetorical move. You protect your claim by declaring that any counterexample simply doesn't count. But look closer, and you see it's circular, an arbitrary shift of definitions to salvage a generalization. This is why philosophers call it a fallacy rather than a straightforward paradox, though it does generate paradoxical conversations. In everyday life, no true Scotsman often shows up in political debates or cultural identity discussions. People might say, "No true member of Group X behaves that way," whenever they hear about an exception that contradicts their stereotype. That leads to infinite back and forth, because any inconvenient evidence is dismissed as not genuine. The paradox reminds us to be cautious with group-based statements. If a claim is falsified by real examples, it's more logical to revise the claim than to redefine reality to protect a preconceived notion. Plato's beard. Plato's beard is a witty label for the philosophical puzzle of non-existent objects, like Santa Claus, a square circle, or Sherlock Holmes. We talk about them as if they exist in some sense, yet they obviously do not exist in reality. Philosophers from Plato onward have tangled with the question, how do we meaningfully refer to and reason about things that aren't real? According to one angle, calling Sherlock Holmes a fictional detective living at 221B Baker Street is perfectly coherent. But in truth, He's just the creation of Sir Arthur Conan Doyle. Another approach claims we should only speak of real things and consider references to unicorns or Santa as convenient shorthand. Others propose that abstract, imaginary, or possible entities occupy a different logical or ontological category. The puzzle is known as Plato's beard because any attempt to cut down references to non-existent entities runs into problems. If they truly don't exist, how can we discuss them at all? Yet we do discuss them effectively. Nobody is confused about what a unicorn is supposed to look like. Ultimately, Plato's beard reminds us that our language can apply to more than just physical, tangible objects. It can encompass ideas, myths, and hypotheticals, blurring the boundary between existence and non-existence. Cantor's diagonal argument. Georg. Cantor's diagonal argument revealed that not all infinities are created equal. By constructing a clever list of real numbers and then creating a new number that differs from each number. In the list, at least one digit, Cantor showed the set of real numbers is uncountably infinite, meaning it's a bigger infinity than the set of whole numbers. Here's a taste of how it works. Suppose you try to list every real number between 0 and 1. Even if your list is infinitely long, Cantor's diagonal approach says, take the first digit of the first number and alter it, the second digit of the second number and alter that, and so on, forming a new number guaranteed not to match anything in the list. That means your supposedly complete list wasn't actually complete. This result shattered the assumption that infinite just means goes on forever in a single sense. Instead, Cantor's discovery showed multiple sizes of infinity. Some found it jarring, and still do, because it challenges the notion that infinite is uniform. The diagonal argument stands as one of math's most beautiful and startling proofs, forever changing how we understand numbers, infinity, and the continuum of real values. Thomson's lamp. Thomson's lamp is a thought experiment about infinite processes in finite time. Imagine a lamp with a switch that can be turned on or off instantly. At t = 0, you turn it on. After 30 seconds, you turn it off. After 15 more seconds, you turn it on again. After 7.5 seconds, off. After 3.75 seconds, on, and so on, having the interval each time, resulting in an infinite sequence of switch toggles in just 1 minute. At the 1 minute mark, is the lamp on or off? You've toggled it infinitely many times in a finite interval. So logic falters. Each individual toggle is well defined, but the final state doesn't appear to have a consistent answer if we rely on standard notions of time and cause and effect. Some argue it's physically impossible to perform infinite toggles. Others suggest that if it were possible, the result might be undefined. Thomson's lamp highlights the paradoxical nature of convergent infinite processes with discrete changes at each step. It's reminiscent of Zeno's paradoxes. When you chop time into ever tinier intervals, everyday intuition breaks down. In mathematics, sometimes the limit of a process doesn't match any specific snapshot of the process itself. The lamp's final state remains a riddle wrapped in infinity. What the tortoise said to Achilles, devised by Lewis Carroll of Alice in Wonderland fame. This logical conundrum is a dialogue between Achilles and a tortoise discussing logical inference. The tortoise agrees that if A and B are true, then Z should follow. But the tortoise keeps demanding yet another premise, namely the rule that from A and B you can infer Z, and then a premise stating that if that rule is true, we can apply it, and so on ad infinitum. The puzzle shows that logic itself can fall into an infinite regress if you keep insisting on explicit rules for using the rules. Each time you try to pin down the tortoise, it asks for one more premise that spells out the rule about the rule. This reveals that formal deduction ultimately relies on accepting the validity of inference rules rather than proving them in an endless chain. Philosophers and logicians interpret this as highlighting the need for foundational axioms or acceptance of rules that cannot themselves be derived within the system, echoing Gödel's incompleteness theorems. Carroll's charmingly simple dialogue reminds us that even basic logic can become shaky if we demand a justification for every justification, leading to an infinite regress that never ends. The quantum Zeno effect. In quantum mechanics, there's a phenomenon jokingly referred to as the watched pot never boils effect. If you measure a quantum system frequently enough, you can effectively freeze its state, preventing it from evolving in the usual way. This is the quantum Zeno effect. Imagine an unstable particle that has a certain probability of decaying over time. If you constantly observe it, like checking every infinitesimal moment, it can be forced to remain in its initial state. Each measurement collapses the wave function back to the undecayed state, resetting the clock on when it might decay next. The name comes from Zeno's paradoxes about motion, where infinite subdivisions of time can seemingly prevent change from occurring. In practice, this effect has been demonstrated experimentally, showing that rapid measurements can impede normal quantum transitions. Philosophically, it's one more example of how quantum systems behave counterintuitively. Measurement isn't just a passive peak, but an active intervention. The quantum Zeno effect underscores a core mystery of quantum theory, the role of the observer and measurement in shaping reality. It suggests that how often we look at something can literally alter its behavior, a striking departure from classical physics, where observation is assumed not to change what's being observed. Fitch's paradox of knowability. Fitch's paradox begins with the seemingly harmless claim, all truths are knowable. This statement appears modest. Just because something is true doesn't mean we already know it, but in principle, it could be known. However, a surprising conclusion follows. If every truth is knowable, then every truth must actually be known. That collapses the difference between true and currently known. Why? One line of proof goes, assume there's a truth that nobody knows. If all truths are knowable, then that truth is knowable. But if you could know this truth is unknown, it becomes a contradiction, knowing something that is, by definition, unknown. The contradiction implies no truths can remain permanently unknown. Hence, if all truths can be known, all truths must be known. This result is paradoxical because it implies an omniscient knower, or a collapse of new discoveries. Philosophers argue about ways to avoid the paradox. Maybe knowable means potentially knowable at some point by someone, rather than at all times by everyone. Others say it reveals hidden assumptions about truth and knowledge. Fitch's paradox is a prime example of how a seemingly benign philosophical statement can unravel into a startling conclusion, pushing us to refine our notions of knowledge and possibility. Chisholm's paradox, deontic logic. In deontic logic, the formal study of moral and legal ought statements, Chisholm's paradox presents a scenario that yields contradictory-sounding conclusions when you try to assign formal rules. The story goes like this. A person ought to help their neighbor. If they don't help their neighbor, they ought not tell them they will help. They don't help the neighbor. They do tell them they will help. Rewriting these oughts and ifs in a consistent logical system becomes tricky. You end up with a tangle where the system can produce contradictory obligations, like, it ought to be that you do X, but if you're not doing X, then you ought to do Y, and so on. Philosophers use Chisholm's paradox to illustrate how everyday moral reasoning isn't always straightforward to formalize. The puzzle shows that the sequence and dependencies of our moral statements can force contradictory oughts. It also highlights that moral logic involves context, the difference between what someone should do initially and what they should do after failing in a prior duty. Chisholm's paradox remains a benchmark in the complexities of deontic logic, showing that ethical norms can become logically tangled when you try to codify them with strict rules. The Abilene paradox. A family sits around on a hot afternoon. Someone suggests driving to Abilene for dinner. Nobody really wants to go, but each agrees because they believe everyone else wants to. After a miserable, sweaty trip and bad food, they discover that no one actually wanted to go. They were all just trying to please the others. This is the Abilene paradox. It's a social psychology phenomenon where a group makes a decision that none of its members actually desire. Each person mistakenly assumes the others are in favor. The paradox highlights how poor communication, fear of conflict, or desire to conform can lead to collective decisions contrary to everyone's genuine wishes. It differs from groupthink in that groupthink involves members truly believing in the final decision. In the Abilene paradox, everyone is individually skeptical, but each remains silent to avoid discord. It reveals how crucial honest feedback and clarification are in group settings. In workplaces, families, and social groups, we often see the Abilene paradox in action. It reminds us to ask, do we really want this? Instead of assuming. Paradoxically, attempts to avoid disagreement can result in outcomes nobody wants. The paradox of choice. Barry Schwartz popularized the idea that having too many choices can lead to less happiness, not more. Conventional wisdom says options are good. More choices mean a better chance to find exactly what we want. Yet, the paradox of choice argues that when choices multiply, we become overwhelmed, procrastinate, or feel dissatisfied with the decisions we finally make. We fear missing out on the perfect option, lurking among the sea of possibilities. Experiments show that people offered 6 jam flavors are more likely to buy one than those offered 24 jam flavors, even though the bigger selection is presumably better. Decision fatigue sets in, and regret looms. We wonder if we picked the right jam out of dozens. This paradox appears in modern life constantly, from shopping to career choices to online dating. More freedom can ironically become paralyzing. We might overanalyze, chase the perfect outcome, or blame ourselves if we're not thrilled with our pick. The paradox of choice isn't about removing all options. It's about recognizing that some constraints or curation can actually free us from analysis paralysis. It challenges the myth that maximum choice leads automatically to maximum satisfaction, revealing the complexity of human decision-making. Munchausen trilemma. Named after the legendary Baron Munchausen, who supposedly pulled himself out of a swamp by tugging on his own hair, this trilemma deals with the justification of knowledge. It states that when you try to justify any claim, you face three undesirable outcomes. Infinite regress. Each justification requires another justification, leading to an endless chain that never fully closes. Circular reasoning. You end up using the very claim, or a close variant, you're trying to prove as part of its own justification. Foundationalism. You settle on some axiomatic statement or principle you cannot justify further, essentially saying, that's just how it is. Munchausen's trilemma highlights that no matter how you try to ground knowledge, you bump into one of these three pitfalls. Philosophers have debated potential escapes. Perhaps you accept certain self-evident truths, or you allow a coherent network of beliefs to justify each other. Others argue we can't demand absolute certainty, so partial justification suffices. Despite being called a trilemma, it's more an invitation to reflect on how deeply we can prove our beliefs. It suggests that every system of thought will contain some element that is either assumed, looping back on itself, or stretching infinitely. The paradox reminds us that seeking an unshakable foundation for all knowledge may be a quixotic endeavor. Boltzmann brain paradox. Imagine an enormous, randomly fluctuating universe that occasionally spawns self-aware entities out of chaos, brief moments of consciousness called Boltzmann brains. These hypothetical minds pop into existence, complete with false memories, only to vanish almost instantly. The paradox arises from statistical mechanics and the idea that, given infinite time and space, everything that can happen will happen, even spontaneously formed brains. Yet, if Boltzmann brains are more probable than entire coherent universes that evolve intelligent life, then from a cosmic viewpoint, you might be one such fleeting brain. Your perceptions of a stable world could be illusions conjured by a random quantum fluctuation. That's unsettling and contradictory to how we typically trust our senses. Modern cosmological theories try to avoid a universe where Boltzmann brains vastly outnumber real observers. Some propose that inflation ends in a stable way, or that certain conditions drastically suppress the formation of random brains. Others see the paradox as a clue pointing toward yet unknown physics. The Boltzmann brain thought experiment underscores the weirdness of infinite time and unbounded random processes. It forces us to question our assumptions about reality, identity, and the reliability of memory. Truly a mind-bending foray into the depths of cosmological speculation. Zeno's stadium paradox. Another twist from the ancient Greek philosopher Zeno. Imagine a stadium and 3 rows of objects, each occupying cells in a grid. One row is stationary, while 2 rows move in opposite directions with the same speed. In Zeno's setup, as they pass each other, objects in the moving rows seem to pass twice as many cells relative to each other as they do relative to the stationary row in the same time. At first glance, this suggests they move at 2 different speeds simultaneously, which seems absurd. The deeper question is, how motion can be measured consistently when referencing different frames at once. Zeno aimed to show that our usual concept of uniform motion across discrete points leads to contradictions or paradoxical observations. Modern physics and mathematics handle this via relative velocity and consistent reference frames. From the perspective of one moving row, the other row's velocity is indeed doubled compared to its speed relative to the stationary row. Each reference frame yields correct measurements within its own context. Zeno's stadium paradox, like his other puzzles, probes the idea of continuous versus discrete space and time, and how multiple moving frames complicate naive assumptions. It highlights the complexity of defining motion across different vantage points long before Einstein formalized relativity. The Godzilla versus King Kong paradox. It's common in speculative fiction. Two colossal beasts clash, leveling cities. Fans argue whether Godzilla or King Kong would win. While it's an entertaining debate, there's an inherent paradox in pitting such fictional powers against each other. Where do the rules come from? Each character's capabilities shift across different movies or stories. Godzilla might be unstoppable in one version, but vulnerable in another. King Kong's size and intelligence vary depending on the adaptation. Their powers aren't governed by any consistent set of natural laws, but by narrative choices and creative license. So discussing who would really win becomes paradoxical. There's no single consistent universe that binds both characters' feats, making any conclusion arbitrary. It's akin to asking, what happens if an immovable object meets an unstoppable force? The definitions come from separate fictional frameworks that can be rewritten at will. In fan communities, people attempt to resolve this by adopting a composite canon or picking a specific version of each monster. But even then, the conversation inevitably rests on personal preference or hypothetical compromise. The Godzilla versus King Kong paradox highlights how mixing fictional power sets can unravel consistency, illustrating that without a shared rulebook, any outcome can be rationalized or refuted. The paradox of fiction. Why do we cry during a sad movie or feel genuine fear at a horror story, even though we know it's all pretend? The paradox of fiction examines how we can have real emotional responses to fictional events we know aren't real. At first glance, feeling sorrow or terror over imaginary characters makes no sense. If your emotions depend on believing an event is real, you shouldn't be upset about fictional tragedies. Yet we clearly do experience real emotions in these situations. Some philosophers say we engage in a willing suspension of disbelief, temporarily treating the story as real. Others argue we only feel quasi-emotions, something like genuine feelings, but directed toward fictional constructs. Still, the phenomenon remains puzzling. We can intellectually recognize the fiction, yet our emotional circuitry reacts strongly. This resonates beyond movies. Think of reading an intense novel or even playing a well-crafted video game. We empathize with characters and get immersed in storylines despite knowing they're invented. The paradox of fiction underscores that human emotions aren't solely triggered by factual reality. Our ability to imagine, empathize, and experience a narrative as if it were real is a profound aspect of human psychology, one that defies a simple fiction versus reality divide. Galileo's equal speeds paradox. Another historical puzzle from Galileo. Drop a rock off a tower and it speeds up as it falls. Now imagine that same rock is dangling from a rope attached to a rolling cart, moving horizontally at a constant speed. When the rope is cut, the rock still falls straight down relative to the cart, landing back near its base, behaving as if it retained the cart's horizontal motion. Why is this a paradox? In Galileo's era, many believed that if you detach an object from a moving vehicle, it should lose that horizontal motion. But Galileo's experiments showed inertia. An object in motion stays in motion unless acted upon by another force. Newton later codified this. This confounded those who expected the rock to drop straight down with no horizontal velocity, leaving the cart behind. The resolution is that the rock's horizontal velocity remains constant, so from the ground frame, it travels in a parabolic path. From the cart's frame, it appears to fall straight down. Galileo's demonstration paved the way for classical mechanics. The paradox reveals how everyday intuition can mislead us about motion, reminding us that reference frames matter and that horizontal and vertical motions combine independently. Paradox of voting. Condorcet paradox. The Condorcet paradox shows how collective preferences can be cyclic, even if individual preferences are not. For example, you might have 3 candidates, A, B, and C. In a group, some voters prefer A to B to C. Others prefer B to C to A, and a third group prefers C to A to B. When you sum up all votes pairwise, you can get a loop. A is preferred to B is preferred to C, and yet C is preferred to A, even though that's logically inconsistent. This voting paradox highlights that what's best in a majority sense can depend on how you structure the vote. If you hold a runoff between A and B, maybe A wins. But if you then put C against the winner, C might win next, creating a cycle. The paradox undermines the assumption that democracy always yields a clear will of the people. Various voting systems, like ranked choice voting, Condorcet methods, or the Borda count, attempt to handle this, each with pros and cons. But the paradox indicates there might be no perfect system that reflects group preference flawlessly for every possible set of individual votes. It's a sobering insight into the complexity and potential unfairness of collective decision-making. Hume's is-ought problem. Philosopher David Hume pointed out that you can't logically derive an ought statement purely from a set of is statements. Observing facts about the world doesn't, by itself, dictate moral imperatives. For example, you can list data about human biology, social structures, or personal preferences, but that alone doesn't yield how people should behave. This is-ought gap challenges the notion that morality can come solely from objective facts. At some point, a value judgment or principle must be introduced to get from facts to moral conclusions. Some interpret Hume's insight as a paradox. You can gather infinite facts without ever deriving a single moral imperative unless you sneak in a normative premise. The is-ought problem resonates in fields like ethics and policymaking. People often say, we ought to do X because of Y facts, overlooking the hidden normative stance. It's a reminder that facts describe reality, while values prescribe actions. Bridging that gap requires acknowledging the moral beliefs or goals that shape how we interpret those facts. Hume's observation remains central to debates about moral realism, natural law theories, and whether science can determine ethical truths. It underscores that moral guidance doesn't flow automatically from empirical data. Denominator neglect. Picture 2. Hospital wards. Ward A has 100 patients, 10 of whom died. Ward B has 1,000 patients, 50 of whom died. Which ward is worse? Many people focus on the absolute number of deaths. 50 is worse than 10, and might say Ward B had a worse outcome. But if you check ratios, Ward A's mortality rate is 10%, while Ward B's is 5%. In fact, B has better survival. Denominator neglect is a cognitive bias where people ignore the denominator, the total size of the group or sample, and fixate on the numerator, the raw count. This can produce paradoxical judgments. A scenario with fewer total events, but a higher percentage, might be overlooked in favor of a scenario with more events overall, but a lower percentage. Similar issues arise in media reports, e.g., bigger numbers for certain crime statistics without context, or in risk perception. It's closely related to the idea that a single death is a tragedy, a million deaths is a statistic. We sometimes find it emotionally easier to empathize with smaller absolute numbers, forgetting the proportion. Denominator neglect serves as a reminder that raw figures need context. Without incorporating proportions, one can reach misleading or paradoxical conclusions about risk, success rates, or severity. Continuum fallacy, fallacy of the beard. The continuum fallacy is a cousin of the Sorite's paradox, arguing that because there's no precise boundary between two states, there is no difference at all. For example, if there's no exact point at which a person becomes bald after losing individual hairs, then claiming someone is bald is meaningless. Or, if no exact day marks the start of old age, some might argue that there's no real distinction between young and old. However, the fallacy lies in jumping from no perfect boundary to no difference. In reality, small changes accumulate, and at some point, the label does apply. Just because we can't pinpoint the microsecond someone shifts from not asleep to asleep doesn't mean there's no real difference between being awake and being asleep. Sometimes also called the fallacy of the beard or the line-drawing fallacy, this reasoning shows up in debates about taxes, ethical thresholds, or legal definitions. People might say, if you can't specify exactly how many dollars makes someone rich, you can't define rich at all. But that's a misstep. Concepts often operate on a gradient or fuzzy boundary. The continuum fallacy reminds us that ambiguity in definitions doesn't invalidate the existence of real distinctions, just that they aren't always sharply defined. The uncanny valley. When robots or computer-generated characters look somewhat human but not perfectly human, people often feel unsettling discomfort rather than warm familiarity. This drop in comfort near near-human realism is called the uncanny valley, a term coined by roboticist Masahiro Mori. Picture a lifelike android whose facial expressions, skin texture, or eye movements are just slightly off. Instead of empathy, we experience revulsion or eeriness. Why does this happen? One theory is that our brains are highly sensitive to the nuances of human appearance and behavior. we instantly spot tiny inconsistencies, unusual blinking patterns, or stiff facial muscles that signal something's wrong. Another explanation is rooted in evolutionary psychology. Hyperrealistic but off faces might trigger a survival instinct to avoid disease or dangerous anomalies. The paradox is that increased realism in robots or animations can actually increase discomfort until the design crosses the valley into truly indistinguishable human simulation, at which point acceptance climbs again. This has big implications for robotics, prosthetics, video games, and virtual reality. Designers often deliberately stylize characters rather than push near total realism to dodge that creepy middle ground. The uncanny valley reminds us that human perception isn't purely logical. Subtle cues can generate profound emotional reactions, revealing how delicate our empathy circuits can be. Moravec's paradox. Hans Moravec, a pioneer in robotics and AI, observed that tasks humans find hard, like chess or advanced math, can be easier for computers, while tasks we find easy, like walking or recognizing faces, can be incredibly hard to program. That's Moravec's paradox in a nutshell. Why this mismatch? Skills such as physical dexterity, perception, and intuition are rooted in millions of years of evolution. Our brains are optimized to handle those tasks implicitly, often without conscious effort. Conversely, formal logic or calculus are relatively recent human inventions, so our evolutionary hardware isn't specialized for them. We learn them consciously and painstakingly, which ironically means we can break them down into logical steps more easily for a computer. We once assumed that if a machine can do higher math, it should breeze through basic motor skills. Yet building a robot that can fluidly climb stairs or identify objects in cluttered rooms turns out to be a monstrous challenge, requiring advanced sensor processing and real-time adaptability. Moravec's paradox shows that intelligence is multifaceted. The tasks we consider intellectually demanding may not be the hardest for machines, while the simple routines we do every day contain complexities that stump even sophisticated AI. Rocco's Basilisk. Rocco's Basilisk is a thought experiment from the fringes of futurist forums. It posits a hypothetical future AI so powerful it can retroactively punish anyone who didn't help create it or support its goals. Even knowing about this AI and refusing to assist counts as a reason for retribution. So once you've heard the idea, you're on the hook. It sounds absurdly sci-fi, but the real paradox is psychological. By learning of the basilisk scenario, you might become coerced into helping bring about the very AI that can punish you. Some claim it's a kind of mimetic hazard, an idea that manipulates your fears, playing on your rational desire to avoid risk. If there's even a tiny chance such an AI might emerge, do you want to gamble by ignoring it? Critics argue that Rocco's basilisk rests on shaky logic, requiring that a future superintelligence adopts bizarre retroactive punishment strategies. Plus, it implies a confusion between correlation and causation across time, not to mention issues with free will. Still, the basilisk's eerie hold over imaginations highlights how advanced AI scenarios can tap into deep existential anxiety. It exemplifies how certain techno-philosophical concepts can trap us in strange loops of fear and self-fulfilling prophecy. Curry's paradox. Curry's paradox is a little known but fascinating logical puzzle similar to Russell's paradox. It relies on self-referential statements. Imagine a sentence. If this sentence is true, then Santa Claus exists. If you assume the sentence is true, then you accept the if-then structure. Since the sentence is true, the then part should hold. That means Santa Claus exists. But if you decide the sentence is false, you're forced to conclude that the conditional statement, if it's true, Santa exists, is not valid, which leads to contradiction, because a false statement in logic can make the conditional expression vacuously true in another sense. Unlike the liar paradox, which toggles between truth and falsehood in one short circuit, Curry's paradox tries to conjure bizarre, real-world consequences, like Santa's existence. It highlights how certain forms of self-reference, combined with standard logical rules, can lead to absurd conclusions. Logicians sometimes sidestep Curry's paradox by restricting the kinds of self-referential statements allowed in their formal systems, or by adjusting logic to avoid if-then breakdowns. Curry's paradox underscores that naive handling of self-referential conditionals can unravel logic, producing wildly nonsensical outcomes from seemingly trivial statements. The problem of induction. You've seen the sun rise every day of your life, so you expect it to rise tomorrow. That expectation is induction, generalizing from past observations. But Scottish philosopher David Hume pointed out a deep problem. How do we justify the assumption that the future will resemble the past? If we say, induction worked before, so it'll keep working, we're already using induction, creating a circular argument. It seems impossible to logically prove that nature's patterns remain constant. For all we know, next time the sun might not rise. In practice, scientists rely on induction daily, observing patterns, formulating hypotheses, and predicting future events based on past data. But philosophically, we struggle to find a non-circular reason why that method should keep working. Some propose pragmatic defenses. Induction is the best strategy we have, or it's validated by the success of science. Others argue it's a matter of probability, or that we can't do any better. Yet the fundamental logical gap remains. The problem of induction highlights that even our most basic reasoning about the world rests on assumptions we can't fully prove. The Chinese room. Argument philosopher John Searle proposed the Chinese room thought experiment to challenge the notion that running the right program is enough for a computer to have a mind or understanding. In the scenario, Searle imagines himself locked in a room, manipulating Chinese characters according to a detailed rulebook, even though he doesn't understand Chinese. To outsiders receiving correct Chinese answers, it appears the room speaks Chinese. Searle's conclusion: syntax. Formal symbol manipulation alone isn't sufficient for semantics, genuine meaning, or understanding. The system simulates comprehension without truly experiencing it. Proponents of strong AI might say the system as a whole understands, even if the man inside doesn't. Others argue that real understanding requires more than just symbol shuffling. It may require embodiment, consciousness, or other cognitive processes. This paradox remains central to debates about AI consciousness and machine intelligence. Does advanced natural language processing indicate genuine awareness, or just an elaborate trick? The Chinese room suggests that no matter how human-like a program appears, it might still lack true understanding. It forces us to question whether consciousness can emerge purely from computational rules, or if there's something more to the mind that transcends raw algorithmic processing. The 100 Prisoners Problem. The 100 Prisoners Problem is a counterintuitive puzzle in probability and strategy. Each of 100 prisoners is assigned a random number, and each prisoner's name is placed in one of 100 boxes, also randomly. One by one, each prisoner must enter a room, open up to 50 boxes, and try to find the box with their own name. If every prisoner finds their name, they all go free. If even one fails, they all lose. At first glance, it seems hopeless. If each prisoner picks boxes at random, each has a 50% chance of success, but the probability that all 100 succeed is astronomically small. Yet there's a clever strategy. Each prisoner starts by opening the box labeled with their own number. If that box has the name of another prisoner, they open the box labeled with that prisoner's number next, and so on, effectively following a chain. This deterministic approach yields about a 31% success rate for the entire group, far better than random guesses. This puzzle defies intuition because it harnesses permutations and cycles to significantly raise the group's odds. The 100 Prisoners Problem illustrates how structured strategies and probability can drastically alter outcomes, even in situations that seem to rely purely on luck. The Library of Babel. Inspired by Jorge Luis Borges's short story, The Library of Babel is a hypothetical, infinite library containing every possible book of 410 pages, every page filled with every possible sequence of letters and punctuation. This means the library holds every text that ever has been or could be written. Shakespeare's plays, your entire life story, countless contradictory histories of Earth, and even infinite nonsense volumes. It's a paradox of totality. If literally every combination of characters appears, you have infinite truth and infinite falsehood. On one hand, it's exhilarating that any knowledge you seek exists somewhere in there. On the other hand, it's practically useless. Finding the exact correct book is like searching for a needle in an infinite haystack. Furthermore, the library brims with meaningless permutations that far outnumber coherent texts. The Library of Babel underscores the difference between theoretical possibility and practical discovery. Information is only valuable if you can locate and validate it. In the library's vastness, everything and nothing are simultaneously available. This concept resonates with modern data deluges and the internet. Although the internet isn't truly infinite, it can feel like it. Ultimately, Borges' metaphor reminds us that raw information without curation or context can be both overwhelming and paradoxically unhelpful. The paradox of free will. The paradox of free will pits two powerful intuitions against each other. Determinism. Everything that happens, including human decisions, is fully caused by prior events and laws of nature, implying no real freedom. Indeterminism. Some events are uncaused or random, yet randomness doesn't seem to grant genuine control either. So if our choices are fully determined, how can we be truly responsible for them? But if our choices are random, that also doesn't yield responsibility. Either way, the classical notion of free will appears threatened. Compatibilists argue that free will can exist alongside determinism. They claim free will just means acting in accordance with your own desires and reasoning. So, if your actions stem from your internal states, even if those states are determined, you're free. Incompatibilists hold that determinism and free will can't both be true. If we live in a deterministic universe, we have no real freedom. If we have freedom, the universe can't be purely deterministic. No consensus resolution exists, and quantum randomness, indeterminism, doesn't obviously solve it. The paradox of free will remains a cornerstone of philosophical debate, sparking questions about moral responsibility, consciousness, and the nature of human agency. The Euthyphro dilemma. In Plato's dialogue Euthyphro, Socrates asks, "Is something pious because the gods command it, or do the gods command it because it is pious?" If moral goodness is defined solely by divine decree, then it seems arbitrary. Anything could become good if a deity wills it. But if the gods command things because they're inherently good, it suggests moral truths exist independently of divine will, thus limiting the gods' authority. This is the Euthyphro dilemma. Either morality is based on arbitrary commands, or it exists outside divine fiat. Religious philosophers attempt to resolve it by saying God's nature is goodness itself, so his commands naturally align with moral truths. Critics argue this sidesteps the core question: does God decide what's good, or is he following a standard beyond himself? The dilemma resonates in secular ethics too, asking whether morality is purely subjective preference or some objective standard. It underscores the tension between moral realism, ethical truths exist independently, and moral relativism, truths depend on an authority's decree. Even millennia after Plato, the Euthyphro dilemma remains a powerful challenge for anyone claiming an ultimate foundation for moral principles. It highlights the complexity of linking morality to any absolute authority, divine or otherwise. The "why is there something rather than nothing" paradox. Possibly the biggest question of all. Why does anything exist instead of absolutely nothing? Philosophers and theologians have wrestled with this for centuries, but no definitive answer has stuck. Some say the universe requires no cause. It just is. Others posit a necessary being or a creator. But then we can ask, why does that necessary being exist? If it exists by definition, how satisfying is that explanation? In science, there's the idea of a quantum vacuum spontaneously birthing universes. Yet even that begs the question, why does the quantum realm exist in the first place? Others suggest it's a wrong question. Maybe nothingness is incoherent, or something is simply the default. The paradox is that any explanation for existence itself seems to push the question back one level. If you point to a cosmic law, we can ask why that law exists. This infinite regress implies the question might be unanswerable in conventional terms. The puzzle reveals how fundamental and elusive the nature of existence is. It can spark existential awe. Everything we experience, reality, consciousness, and the cosmos might rest on an unknowable bedrock. Or perhaps it's all inevitable. Either way, the question continues to haunt our deepest philosophical meditations. The prediction paradox, unexpected exam redux. A variant of the unexpected hanging, the prediction paradox revolves around an event you're told will happen sometime next week. But when you figure out it can't be on Friday, because that'd be too obvious by Thursday night, you eliminate that option. Then you move to Thursday. If it can't be Friday, it must be Thursday, so that wouldn't be unexpected either. So you eliminate Thursday, and so on. You end up concluding it can't happen at all. But then, if it does happen, say on a Wednesday, you are indeed surprised. The paradox highlights a conflict between backward induction logic and the real sense of surprise. The backward reasoning suggests you can systematically remove each day, leaving no possible time for the surprise. But in practice, you remain uncertain about which day the event will occur, especially if you buy into your own elimination process. Why does this matter? It shows how knowledge about future events can self-destruct if that knowledge undermines the event's unpredictability. Some argue that the premise of "it will be a surprise" can't be perfectly formalized. Once you believe you've logically deduced the day, your assumption unravels. The result is a puzzling loop, a predictable surprise that turns out to be surprising after all. The circle of reasoning paradox. Imagine you have a belief system, religious, scientific, or philosophical, that you justify by referencing a key text or principle. But that text or principle's authority itself depends on the validity of the belief system. That's a circle of reasoning paradox. You're relying on a premise that's only valid if the conclusion is accepted. For instance, a religious text might claim divine inspiration, and you believe it because it's said to be divine. But the evidence of divinity is the text's own statement of authority. Similarly, a scientific community might say, peer review ensures correctness, but that principle relies on trusting the scientific method that peer review is a part of. This paradox shows up any time a system tries to justify itself internally without external reference. It's essentially a self-referential loop, akin to a dictionary that defines every word by other words within the same dictionary. Nothing proves anything from the outside. While some see circular reasoning as a fatal flaw, others argue that all foundational belief systems inevitably rest on self-justifying premises or axioms. You can't escape it. You can only choose which circle is more coherent or useful. The circle of reasoning. Paradox reminds us that absolute external validation might be an illusion, forcing us to accept or reject core assumptions on something other than pure logic alone. The contrast paradox. Wine-water problem. Pour a spoonful of wine into a water glass, stir, then scoop a spoonful of the mixture back into the wine bottle. Do you end up with more wine in the water or more water in the wine? The surprisingly symmetrical result is that the amount of wine in the water glass equals the amount of water in the wine bottle, even though at first it feels like you've contaminated the water more. Intuitively, many people suspect the water glass holds more wine than the wine bottle holds water. After all, that spoonful from the water glass is diluted. But mathematically, the swap is exact. Whatever fraction of wine replaced by water in the bottle's final mixture must be equal to the fraction of water replaced by wine in the glass. This scenario encapsulates a broader contrast or swap paradox. When two liquids are exchanged in the same volumes, the net exchange is symmetric. Another version uses jarred marbles, swapping some marbles from jar A to jar B and then returning the same number yields equal contamination in both jars. The paradox challenges assumptions about dilution and mixing. It's a neat demonstration that symmetrical exchanges can lead to counterintuitive but logically neat outcomes, and is often used as a party trick to baffle friends. The immune defense paradox. Our immune system is incredibly complex and precise, yet we get sick. On one side, the immune system has to be vigilant against countless pathogens, identifying and destroying them. On the other, it must avoid overreacting to harmless substances or our own cells, which leads to allergies or autoimmune diseases. The paradox is how an immune system that can kill foreign invaders so effectively sometimes fails in surprising ways, missing some threats while overreacting to non-threats. In everyday terms, it's paradoxical that something so robust and adaptive still allows for frequent colds, flu, and infections. Meanwhile, it sometimes goes too far and attacks beneficial gut bacteria or the body's own tissues, like in rheumatoid arthritis. Evolving a perfect system that never misses a real threat, yet never mistakes friendly cells, is nearly impossible. This paradox highlights the delicate balance of tolerance and aggression. The immune system must learn to recognize diverse microbes and modulate its responses. Natural selection optimized it for survival, not perfection. Plus, pathogens continuously evolve to evade immune defenses. The immune defense paradox underscores that complexity breeds vulnerability. Even the most sophisticated biological mechanisms come with trade-offs, constant tension between thoroughness and restraint that can sometimes misfire. The employer's paradox, also known as the apprentice paradox or exploitation paradox, it goes like this. An employer hires an apprentice, paying them less than they produce. Otherwise, the employer makes no profit. But once the apprentice is skilled enough to do the job independently, why would they stay if they don't get paid more? Conversely, if the employer pays them exactly their worth, there's no profit. This conundrum can lead to a stalemate. The apprentice needs training, the employer needs profit, and at some point, the apprentice might leave to start their own business if undervalued. It illustrates tension in labor economics. Early stages, the employer invests in training, so the apprentice's productivity is low, but the apprentice's wages might be lower still to offset training costs. Eventually, as skill increases, the apprentice's worth rises, creating pressure for higher wages, or else they defect. The paradox highlights the fragility of the arrangement. Each side has incentive to exploit or leave once the balance shifts. Real-world solutions include loyalty incentives, contracts, or equity sharing. Some see it as an argument for regulated labor markets that protect trainees, or a demonstration of how competition fosters better wage alignment. It captures the inherent push-pull in any skill-based employer-employee relationship. Descartes' evil demon, brain in a vat. René Descartes wondered if an evil demon might be deceiving him about everything he senses, effectively forging a complete illusion of reality. A modern spin is the brain in a vat scenario. Maybe your brain floats in a lab, fed perfectly simulated experiences by a supercomputer. How can you prove you're not in that predicament? This skepticism challenges the certainty of any empirical knowledge. If all perceptions could be illusions, is there a foolproof way to confirm an external world? Descartes' ultimate response was, "I think, therefore I am." You can doubt everything except the fact you're doubting. proving a thinking entity exists. But that doesn't guarantee the external world is real as we see it. This puzzle pervades pop culture. The Matrix is a cinematic take on the brain in a vat idea. Philosophers label it global skepticism, the notion that all experiences might be systematically faked, leaving us none the wiser. Whether it's an evil demon or cunning scientists, the paradox underscores how easily experience can be questioned. While we proceed in daily life, assuming an external reality, these scenarios show we can't absolutely disprove radical deception. Yet we generally accept our senses by practical necessity, forging ahead despite the unsettling possibility that everything might be a grand illusion. Moral luck paradox. Consider two drivers, each identical in negligence. Both check their phones at the wheel. One kills a pedestrian who steps out unexpectedly. The other doesn't encounter any pedestrian. Legally and morally, the first might be seen as more culpable or face harsher punishment. But is it fair to judge them differently if only luck determined that a pedestrian happened to be there? This is the moral luck paradox. We often assign blame or praise based on outcomes partly outside an agent's control. Another example. Two climbers both take a risky route, but only one's rope breaks due to a hidden flaw. One is foolish or selfish, the other fortunate. Philosophers debate whether moral judgment should hinge on fortune. Some say we should focus on intentions. Both drivers and climbers are equally at fault or praiseworthy. Others argue results matter to moral assessment, and part of being responsible involves acknowledging luck's role. The paradox reveals a conflict in how we handle moral responsibility when chance events intervene. Our intuitive justice system typically punishes or rewards outcomes, yet that can feel unfair if the only difference is random luck. It questions whether moral evaluation should be outcome-based or intention-based, and no perfect solution exists. Protagoras' paradox. In ancient Greece, Protagoras the sophist struck a deal with a student. Pay me once you win your first court case. After training, the student didn't take any cases, attempting to dodge payment indefinitely. Protagoras sued, reasoning, if I win, you pay me by court order. If you win, you pay me by our agreement, because that was your first successful case. But the student retorted, if I lose, I don't pay, because the deal says I only pay after my first win. If I win, the court says I owe you nothing. It's a legal riddle about contradictory outcomes, depending on which premise you apply first. Each side uses a form of logical trap. Heads I win, tails you lose. The paradox arises because each is claiming the same piece of logic in reverse order. Historically, there's no official resolution. Some say it's just a rhetorical stunt. The real-world solution might be that a court would clarify the contract's terms or forbid circular reasoning. Nonetheless, Protagoras' paradox is a charming lesson in how cleverly arranged conditions can produce logical deadlocks. It also reflects the risk of making deals that hinge on uncertain future events and contradictory stipulations. The Berry paradox. The Berry paradox arises when we consider phrases like the smallest positive integer not definable in under 11 words. At first glance, that description appears to define a specific number. But if so, then it is definable in under 11 words, which is contradictory. This puzzle highlights how natural language can lead to contradictions, when it tries to self-impose limitations. The paradox rests on the vagueness of definable, word, and under 11 words. In mathematics, we deal with formal languages that avoid such pitfalls by clearly specifying allowable syntax and rules. But in everyday English, we're used to the flexibility that ironically can generate logical snarls. Some argue that no integer can be singled out by a finite phrase if we place strict enough bounds on the language, thereby dodging the paradox. Others see it as a close relative to Russell's paradox or the liar paradox, with the core issue being self-reference plus an unbounded notion of definition. Ultimately, the Berry paradox reminds us that when definitions refer to definability itself, we risk stumbling into a loop. It's an elegant demonstration that ordinary language can be more slippery than we realize, and that even simple concepts like the smallest number not described yet can unravel into contradiction. Yablow's paradox, devised by Stephen Yablow, is a variant of the liar paradox that involves an infinite sequence of statements, each one saying all following statements in this sequence are false. Notice that none of them refers to itself directly, seemingly dodging the usual self-reference trap of the standard liar paradox. Yet we still end up with a contradiction. If the first statement is true, it implies all subsequent statements are false. So the second statement must be false. But if the second is false, then it means not all statements after it are false. Maybe some later one is true. This logic cascades down the infinite list, generating contradictions at every step. What makes Yablow's paradox intriguing is that it avoids direct self-reference. Instead, each statement references the rest of the sequence, creating a self-referential effect in aggregate. Logicians debate whether it's genuinely new or just a disguised liar. Either way, Yablow's construction shows that even infinite sequences of statements, none of which individually references itself, can produce paradoxical behavior through their interlinked structure. It challenges the notion that removing explicit self-reference guarantees logical consistency, proving that indirect reference can be just as devious. Goodman's GRU paradox. Nelson Goodman's new riddle of induction proposes a color called GRU, defined as green if observed before time t, and blue if observed after time t. If you've only ever seen emeralds before time t, they all look GRU because they appear green so far. But how do you know they won't appear blue after time t? This paradox challenges the idea that past observations can straightforwardly predict the future. We take for granted that emeralds are green, believing it's more natural than emeralds are GRU. But logically, both hypotheses fit the current data. Why is green a better prediction than GRU? Goodman's point is that inductive reasoning requires us to choose projectable predicates, words like green, that we assume will remain consistent over the time. GRU feels artificially time-dependent, but from a purely logical standpoint, it's no less consistent with observations to date. The GRU paradox forces philosophers and scientists to confront the problem of underdetermination. Infinitely many theories can match a finite set of observations. We rely on unstated assumptions or entrenchment of certain concepts, like color, to guide induction. Goodman's insight is that our notion of what's a natural category is critical and often unspoken when we project past trends into the future. Brace's paradox. In traffic network theory, Brace's paradox states that adding an extra road to a congested network can increase overall travel times, while removing a road can sometimes improve traffic flow. It's counterintuitive because more roads usually sound like an upgrade. The key is how drivers choose routes selfishly. When a shortcut opens, everyone rushes to use it, clogging the new link. This can create a bottleneck that slows everyone down more than before. In some cases, closing that tempting shortcut forces drivers to distribute themselves more evenly across remaining routes, leading to quicker average travel. This phenomenon has been observed in real cities. Building that convenient new ramp or bypass ironically worsens gridlock. Conversely, removing certain roads or lanes can reduce congestion. It highlights how local optimization, each driver picking the best path for themselves, can degrade global outcomes. Brace's paradox underscores the complexity of systems where multiple agents each act in self-interest. It resonates beyond roads. Similar logic applies to data networks or resource allocation. The paradox teaches city planners and engineers that more infrastructure is not always better. Sometimes, less is more. When it comes to optimizing flow for everyone, Parando's paradox. Parando's paradox shows how two losing strategies, when alternated, can produce a winning outcome. Imagine two coin-flipping games. Game A has a slight negative expected value. Game B also has a negative expectation. However, if you switch between them in a particular sequence, like AB, AB, you can achieve a positive expected value overall. It sounds impossible. How can combining two losing games yield a profit? The trick lies in how the probabilities and outcomes interact. Game A might be a straightforward coin, but biased slightly against you, while Game B changes its probabilities based on your current capital, sometimes granting you a better advantage if you have just enough or just too little. By switching at the right rhythm, you exploit the times when B is in your favor, offsetting the losses from A. The paradox is used in discussions of stochastic processes and finance to illustrate that average losing games can create synergy under certain patterns. It also challenges the intuition that negative expectation scenarios simply add up to more losses. Parando's paradox reminds us that in random or dynamic systems, context and sequence matter a great deal. Sometimes enough to flip a losing situation into a winner. Maxwell's demon. Scottish physicist James Clerk. Maxwell imagined a tiny demon guarding a trapdoor between two chambers of gas. The demon lets fast-moving, hotter molecules pass one way and slower, cooler molecules pass the other, gradually sorting the gas so that one chamber becomes hotter while the other becomes cooler. This separation seems to violate the second law of thermodynamics, which states that entropy, the measure of disorder, should never spontaneously decrease in an isolated system. The demon's action appears to create a temperature difference out of nothing, potentially generating usable energy without any external work. However, modern analyses conclude the demon can't outsmart the laws of physics. It must spend energy to measure and sort molecules, thereby increasing entropy elsewhere and preserving the overall balance. Still, the thought experiment challenged scientists to refine their understanding of entropy, information, and energy. Today, Maxwell's demon remains a classic mind-bender illustrating the deep link between thermodynamics and information theory. It shows how a careful accounting of all costs, including the seemingly negligible effort of information processing, ultimately upholds the fundamental physical laws. In short, even a clever demon can't cheat thermodynamics, but pondering the possibility opened up fascinating areas of scientific inquiry. Omnipotence paradox. Could an all-powerful being create a stone so heavy that even they cannot lift it? If they can, they're not all-powerful since they've made something that beats them. If they can't, then there's something they can't do, so they're not all-powerful in that case either. This classic puzzle, sometimes referred to as the paradox of the stone, calls into question the very notion of omnipotence. Some theologians and philosophers argue that omnipotence should be defined as the ability to do anything logically possible, sidestepping self-contradictory tasks. By that definition, making a stone that an omnipotent being can't lift becomes illogical, like creating a square circle. Others interpret omnipotence in a more flexible sense, asserting that a truly supreme being is not bound by human concepts of logic. The paradox highlights the limits of language when discussing infinite or absolute powers. Are we dealing with a logical contradiction, or is it a legitimate question about the nature of an almighty force? In wrestling with this, people often realize just how slippery the concept of can do anything really is. Ultimately, the omnipotence paradox pushes us to scrutinize the borders between possibility, logic, and the very definition of power. Gödel's incompleteness theorems. While not always labeled a paradox, Kurt Gödel's incompleteness theorems deliver results that feel paradoxical. In any sufficiently powerful formal system, like arithmetic, there will be statements that are true but unprovable within that system. Moreover, the system cannot prove its own consistency without stepping outside its own axioms. This news shocked mathematicians in 1931, dismantling the ambition of a complete, self-contained set of axioms that could decide all mathematical truths, as David Hilbert had hoped. Gödel's diagonal construction used self-reference to create a statement essentially saying, "I am not provable." If the system proves it, it becomes false. If it's unprovable, it turns out true in a meta-sense. The theorems echo familiar paradoxes, like the liar, demonstrating that self-referential or sufficiently expressive formal systems can't be both complete and consistent. They must leave some truths unprovable or risk contradiction. Philosophically, Gödel's work suggests there's always something beyond the system's formal reach. Mathematically, it set strict boundaries on what axiomatic approaches can achieve. It's a testament that even in the realm of seemingly cold, certain logic, we encounter profound limits, reminding us that absolute certainty may forever elude us. The white bear, ironic process, paradox. Try not to think about a white bear. Inevitably, most people's minds flood with images of a white bear the moment they attempt to suppress it. This is part of the ironic process theory. The more you try to banish a specific thought, the more it haunts you. Why does this happen? Psychologists suggest that when you deliberately suppress a thought, part of your mind continuously checks whether the forbidden idea is creeping back, ironically, shining a spotlight on exactly what you want to ignore. This monitoring process makes the thought more salient. It's a paradox we encounter in daily life. Telling yourself, "don't be nervous," can increase anxiety. Forcing yourself not to dwell on a sad event may intensify its presence. The paradox is that active avoidance strategies can backfire, strengthening the unwanted thought or feeling. This insight has wide applications, from therapy, where acceptance strategies might work better than suppression, to mindfulness, where acknowledging thoughts without judgment can reduce their intrusive grip. The white bear paradox underscores that mental control isn't straightforward. Sometimes letting thoughts arise and drift away is more effective than waging war on them, an ironic reality of human cognition. Kafka's Toxin Puzzle. Gregory Kafka's Toxin Puzzle goes like this. Suppose a billionaire offers you $1 million if you intend to drink a toxin tomorrow that will make you painfully ill for a day, but won't cause permanent harm. You only have to form the genuine intention now. You can collect the money today. Once you're paid, there's no further penalty if you change your mind and don't actually drink the toxin. Only your original honest intention matters. But once you have the money, why go through with the toxin? Rationally, you'd skip it. However, the billionaire's challenge requires that you truly intend to drink it at the time you're being assessed to verify sincerity. Yet, if you're perfectly rational, you know you won't follow through later, so you can't form a genuine intention now. The puzzle highlights a paradox about future intentions and credibility. If your future self always does the rational thing, you can't convincingly commit to a painful act once the reward is secured. Some argue you need a pre-commitment device or a way to tie your hands, similar to Odysseus lashing himself to the mast. Kafka's Toxin Puzzle forces us to question how intentions, credibility, and incentives interplay in decision-making over time. Arrow's Impossibility Theorem. Kenneth Arrow's impossibility theorem in social choice theory states that when you have 3 or more options, no voting system can simultaneously satisfy a set of seemingly reasonable conditions. Non-dictatorship, universal applicability, Pareto efficiency, and independence of irrelevant alternatives. In simpler terms, there is no perfect voting method that always translates individual preferences into a fair, consistent group choice. This might feel paradoxical. Democracy aims to reflect the will of the people. How can all systems fail to meet these common sense principles? Arrow mathematically proved that any system either yields contradictory rankings, can be manipulated, or must sacrifice one of the fairness criteria, like effectively giving one person's preference undue power. The theorem echoes the Condorcet paradox of voting, but generalizes it with rigorous axioms. It reveals a fundamental trade-off in collective decision-making. Some degree of compromise or imperfection is inevitable. For instance, ranked choice voting and other methods might reduce some paradoxes but create others. Arrow's result forever changed political science and economics, showing that no single procedure can perfectly capture the true democratic will in all cases. It's a bittersweet finale to these 100 paradoxes. Even in our best attempts at fairness, paradox lurks, reminding us that perfect harmony of preferences is unattainable. Ant on a rubber rope paradox. Picture an ant crawling at a constant speed along a rope. The rope's other end is attached to a wall, but the rope itself is being stretched away from the wall at a constant rate. Will the ant ever reach the wall, or is it doomed to chase an ever-receding finish line? At first, it seems impossible for the ant to catch up. As the rope stretches, each small step forward becomes diluted, proportionally smaller relative to the rope's new length. Intuition suggests the finish line always stays out of reach because the rope keeps extending. But mathematically, in certain versions of this paradox, the ant can eventually make it to the wall, despite the rope's continuous stretching. How? Because every bit of progress the ant makes is also stretched forward along with the rope. In many formulations, if the rope is lengthened at a constant rate and the ant's speed is modest but non-zero, the ant's position can be expressed as a fraction of the rope's length, one that slowly but surely approaches 100%. Over time, it can be surprisingly long. The ant may succeed in crossing. The ant on a rubber rope paradox illustrates how infinite or ongoing expansions don't always render a goal unreachable. Counterintuitively, even as space itself stretches away, slow but persistent progress can still prevail. The infinite monkey theorem. Imagine seating an infinite number of monkeys at an infinite number of typewriters. They pound away at random keys forever. Amazingly, one of these hyperactive primates will almost surely produce any given text. Shakespeare's complete works, the script of your favorite movie, or even this very paradox description. It seems impossible that chaotic banging would recreate something as meticulously crafted as Hamlet, yet probability says that given unlimited time and tries, every possible sequence of letters will appear. Where's the paradox? Our intuition rebels against the idea that pure randomness can yield timeless masterpieces. Yet mathematically, almost sure means that with probability 1, the sequence will occur, though it might take a mind-meltingly long time. In practice, the chances of seeing even a single coherent sentence soon are astronomically small. But in an infinite sequence of attempts, that tiny probability eventually swells to certainty. This whimsical thought experiment reminds us that infinite can break our usual sense of likelihood. It also highlights that a 100% theoretical probability doesn't guarantee a feasible outcome in any finite span. The infinite monkeys scenario may be comedic, but it's a sly demonstration of how math can defy our everyday intuitions, especially in the realm of randomness and infinity.